So what's up, bro? In this video I would discuss one of my idea which is related to vernier calipers. So vernier calipers, failed ideas part 1. Now vernier calipers, we all have seen this old looking instrument in our practical labs, most probably physics experiment lab, and we did it in class 9, 10 or 11, 12 I guess. Yeah. And this looks like an old instrument, like the way teachers introduced it to us. I found it very boring. Like, don't we have digital instruments or something else to measure length? Why is it so useful? Like, what's the like? Yeah, I do know the formula of length equals MSD plus MS main scale reading plus least count into vernier scale reading. But yeah, cool. But why is that important? Why is that so important? What actually is the benefit of using vernier calipers instead of, I don't know, some other method to measure length? So yeah, why do we still use it in 2023? Now, I did a lot of research on this because of a question I had. I would tell you the question later on this video, but so I'm gonna pour it all in on you. So let's see how we measure length in the first place. So suppose we have this blue rod and I wanna measure the length of it. So how we normally do it is that I place my 0 against one end of this blue rod and I measure how long this rod and then place it along the rod parallel to the rod. So now this number indicates me the length of the rod. So now as you can see, the length is approximately 2, or you can say 3, and but it's between 2 and 3. I can't exactly say if it's 2 or if it's 3, and that is the problem or the accuracy problem of this scale. Or I can say that the least count of this scale is not enough to give me a good enough approximation of the length of this value. Now if I want to work with large values, I can round off a bit and 2 is acceptable in some cases, but if I want more accuracy, what I can do is I can add 10 more divisions within each of these divisions to increase the accuracy. So like this. Yeah. So now as you can see, between 0 and 1 or 1 and 2, every digit there are 10 more divisions which increase my accuracy. So now before I can say it was approximately 2, but now I can say the length of this the length of this rod is 2.3 something. Now you can still see it's between 23 and 24, but it's acceptable for me now. I can say it's 2.3 centimeters and it's enough for me. So as you can see, by adding 10 more divisions within each division, the accuracy increased by 10x, or I can say the least count decreased by a factor of 10. So before the least count was 1 centimeter and now the least count is 1 millimeter or 0.1 centimeters. So what if I want more accuracy? What if 2.3 is not acceptable to me? So one thing I can do is repeat this process again and add more divisions within each of these, but that would be horrible. Look, it's so horrible that my video is not rendering so good. So you can see I added like 10 divisions within each millimeter, and as you can see, this is the zoomed version of it. Sorry for the video quality, guys. I can't really seem to find another way. So as you can see, now I can say that it's 2.3 less than 5. It's almost, as you can see here, it's almost 2.33. So it's 2.33 meters. And even now as if I'm zooming in, it's really hard for me to see. It's really hard for me to like actually see these with naked eye. I would have to use microscope or like squint very hard. or like squint very hard. So hard to make it digitally. Imagine how hard that would be to get to like add 10 divisions within each millimeter. How hard that would be to physically do it on a physical scale. So it's almost impossible, and you can see it gets so cluttered. It's horrible. It's horrible to look at. So it's a mess. Now this is where the vernier calipers comes in. The ingenious idea of vernier calipers. Look, when I actually studied what vernier calipers can do, the only thing I could the only thing I could think was, man, whoever invented this shit, he's a genius. He is a genius. Like, for example, see here, what we do is, just like in the previous case, I have this blue rod that I want to measure the length of. I stack it against my main scale, so 0 lies on one end point, and then the scale is parallel to the rod. So as you can see that the length of the rod is between 1.1 and 1.2, somewhere in between. So this is the so the limit of my main scale is 1 millimeter or 0.1 centimeter. Now what I do is, the idea of vernier calipers is that I use a scale of 0.9 millimeters or 0.09 centimeter, which is approximately equal to how this small scale is. So this division is 1 millimeter and this division is 0.9 millimeter, which is approximately equal. So it's not as hard to see. I don't have to squint so hard like in this previous case, but it's 0.9 it's 0.9 millimeter and it's acceptable level of shot, I can say. Yeah. So the idea behind it is, I push my vernier calipers just next to the rod I want to measure the length of, so that it's 0 is just next to the length of the rod, just next to the end of the rod. And by virtue of the fact that these divisions are 0.9 millimeters and these are 1 millimeter, so you can see every main scale division is between two vernier scale divisions, and every vernier division is between two main scale division. It's not that, like, it's not possible that two vernier scale divisions are between one main scale or vice versa. So by virtue of this fact, I can say that since this 0 is just ahead of my 1.1 or 11 millimeter division, by the virtue of the fact that it is 0.9 millimeters, there would be at least one division that is approximately coinciding with my main scale, with my some other main scale division, and that main scale division would be, and the number of main scale divisions would be equal to the number of vernier scale divisions. What that means, let me unpack that. What I mean by that is, suppose I want to measure the length x of this rod, and from 0 till here where the vernier scale is coinciding with the main scale is L, and this is Z. So I can say by normal algebra that x is L minus Z. Now I can write Z as n times VSD, or n times, these are like n divisions, 1 2 3 4 5 divisions, and the length of all these divisions is 5 times 0.9 millimeters or 4.5 millimeter, and the length of these is almost 1.6. So L is almost 16 millimeters, right? Now by the virtue of the fact that this is 0.9 and this is 1, I can expand my L as A plus N, or I can say that the division that is just behind the rod, or the division that marks the limit of my main scale's that marks the limit of what my main scale can measure, which is 11 millimeter. If I didn't have this vernier scale, 11 millimeters is what I would conclude that the length of my rod is. So that is, so suppose that is MSR or A, plus which division? N is the division which is coinciding with the main scale. So what I can say is that number of divisions on vernier scale would be equal to the additional number of divisions on main scale. So if this is 1 2 3 4 5, then this would be 1 2 3 4 5. Now a proof can go a little bit. Why is this exactly 5? I have been trying to explain it, but you don't have to understand everything. So overall, what I can write is L is A plus N times MSD plus N times VSD. Sorry. Minus N times VSD. N time A plus N times MSD minus N times VSD. So A times MSD is nothing but 11 millimeters, which is my A, plus N times 1 MSD minus 1 VSD, which I can write as the least count of the vernier scale, which is 1 minus 0.9 mm or 0.1 mm. I can replace the least count with 0.1. So as you can see, I can, what this means is, to really appreciate what this actually does is, I have two scales of least count 1 millimeter and 0.9 millimeter, and using these two again and using these two with each other, I achieved the accuracy or the least count of 0.1 mm. Can you imagine that? I have a scale of 0.9 mm, the least count is 0.9 mm, but the accuracy I am achieving with it is 0.1 mm. That is the ingenuity of vernier calipers. So now I can measure it as 11 mm plus 1 2 3 4 5 5, so least count is 0.1, so 0.5. So I can say that the length of this rod is 11.5 millimeters or 1.15 mm, 1.15 centimeters. So I got that extra digit at the last, which is a huge improvement. And that is exactly why we are taught vernier calipers in our schools, because this allows us to achieve what essentially this allowed us to achieve. Like, if the accuracy that I'm getting with this, and it looks worse, it looks messy, I can't actually see it without using a microscope, and I can achieve this level of accuracy with this. Whoa, when I actually read and understood what it exactly means, I was blown away. But I had this question, and I asked this to my teacher, that is it necessary that one of the vernier division has to coincide with the main scale division? What if no division coincides? And the teacher wasn't really bothered with it, so she said, no, it's not possible. At least one division would coincide with it no matter what. So, but I didn't actually believe it. I didn't want to believe it, because if that was the case, that one of the division has to always coincide, but then that would mean that the division that is coinciding is the length of the scale, is the length of this rod. But if that would be the case, then vernier scale would give always wrong readings. So that is not possible. So even here you look, this division is almost coinciding, the fifth one, and the sixth one is also a little bit coinciding. So if I just move my scale a little bit, now fifth would go far away from this and sixth will coincide with this main scale division. So I can say that for now none of these divisions are coinciding exactly. It's like in between these two. So this prompted me to have an idea. So essentially what vernier scale is allowing me to do is find this distance, right? by, I mean, I was already having this L, but now since I have this N or Z, I can use it. I can use algebra to find this little distance using Vernier scale. Now, what if I use, what if I stack? I had this idea. What if I stack another Vernier scale on top of this so that I can find this distance, and maybe use, and you can, just apply the same principle. 10 Vernier scale divisions equals to 9 this Vernier scale divisions, and here it is. I thought it like this. So I made a longer Vernier scale for some reason you don't have to understand for now. So the idea I had was, here it is 1.1 millimeters, and so here it is 1.1 millimeters. Vernier scale stacked against my rod, and the fifth division is coinciding with it, with the main scale. So now essentially what I thought of doing was to add another vernier calipers of least count 0.81 mm, 0.9 the whole square. So 0.81 mm least count vernier calipers I add on top of this and stack it just equal to this. As you can see, vernier scale is just a little bit ahead and the main scale is just a little bit before. So I stack my second vernier calipers just on the top of main scale. So I have this distance that I can measure using my scale. So how I thought this was, say this is L just like before and this is W, right? This is Z and this is red Z. This is Z and this is Z. So what I'm essentially doing is I want to find the length of this, right? You can say okay, I will explain it like this. The vernier scale reading that is coinciding here is 1 2 0 1 2 3 4. So but it's not exactly 4, as you can see. It's 4 minus something, right? It is like the vernier scale reading that is actually coinciding with, that should have actually coincided with the main scale, was not 4 exactly. It was not an integer. It was maybe 3.8, 3.7 something. So that is what I need to find here. How would I find it? So I need to find W, which is this distance between the end of this rod and this main scale, and this main scale reading here, this red scale here, red division here. So how do we do it? I take Z, which is the division coinciding, which is the vernier division or the vernier length coinciding with the second vernier scale, and Z from 0 to here, and apply that same principle of Z minus Z, multiply by the least count of this vernier caliper second to get W, and then use this same principle of A plus 0.1 times N, A plus N times MSD minus N times VSD to, and plug it in to get this, because this would become Z, because length would become A plus W, and the length would become A plus W, Z would be 0.9 times W, and small z is Z. So I would have this. So now I have the accuracy of 1 mm, 0.1 and 0.01 mm. You can see I had, the scale is 0, the least count of this scale is 0.81 mm, and this is 0.9 and this is 1. So stacking these three give me the accuracy, the least count of 10 raised to power minus 3, which is huge. You can imagine what accuracy this gives me, an accuracy of 10 raised to power minus 2. and it looks so horrible. So to achieve the accuracy of 10 raised to minus 3 here in this scale, I would have to add 10 more in between these, which which is almost impossible to make physically, but I can do it using this. And it's a great invention. I thought I had such a good breakthrough. I thought I would maybe start a manufacturing company and manufacture these vernier scales to sell in schools and boast off to my physics teacher, and you didn't listen, right? But the problem was the idea is wrong. It's not exactly wrong, but the idea has a limitation. What? The problem is that when I first thought this idea, I just like I didn't do the exact mathematical calculations. I just thought, okay, this is related to this and this translates to this, so I just wrote this formula without actually mathematically deriving it. So when I sat down to actually so when I thought, okay, I have a good idea, now I need to patent it, so I need to actually write the whole mathematical derivation down, so that I can actually patent this idea. Then I got this. This is a little bit blurry, you don't have to understand it all. I drew it in my phone. So the thing is, once I did the calculation here, you can see the final result. L is a plus 0.1 m, just like here, minus 0.09 mm. Here I thought it was 0.01, but here it is 0.09, and that makes a huge difference. Now the accuracy is still increased a little bit because of this 0.09 factor, but it's not much. It's just a little bit increase in accuracy, because 0.09 is approximately 0.1, so that doesn't make much of a difference, And I was devastated when I found out about it. Like, I had did so much hard work, I read so much. The derivation I saw you in this one, this derivation, I actually came up with it all by myself. I didn't read it in a book or something. The book had a little bit different derivation. I don't know. I don't exactly remember what the derivation in book was. So I came up with that all by myself, just because I was so invested in this idea, only to find out that it's not much. The accuracy increased is not much. Now, I haven't exactly given up on this idea. I still think it has value, and maybe someday I play with it a little bit and maybe find a breakthrough and patent it. So it's not a dead idea, and don't steal it. I'll sue you. So this is a little joke I wanted to make after I invent my own version of vernier calipers. So stacking 10 vernier scales on each other to measure up till 10 raised to power minus 14 meter accuracy. 10 raised to power minus 14. Can you imagine? It's picometer level accuracy. 0.000 till 14.1. It's so small that you can't even measure. Even the best microscopes fail to measure that kind of accuracy. And that is exactly what we need to measure the size of your dick. So that is all for this video, guys. I hope you enjoyed it, and I hope to carry all the emotions I had while working on with this. The thing was, it was like a ride. I learned a lot about vernier calipers, how and why we measure things, and how we measure length, how we measure things. It was a great learning experience for me, but sadly I couldn't find an idea to patent. I thought it was a great I thought it would make a great invention, and I'd patent it and maybe start a business, and this would change my life. I will become a millionaire, a billionaire, a manufacturing company of vernier scales. But sadly, it didn't put off. So, okay, but sadly, it didn't work out. And you should take inspiration with this. It's not always gonna work out. It's not always gonna work out. You get so excited that you don't actually think it through. And when you do think it through, you find out it was wrong. And don't give up. It's okay. It's okay it was wrong. The whole journey was fun. It was fun working on this idea. And I learned so much. It's enough.